Chapter 3.1, we're looking at a lot of different things in this chapter, starting with the domain of functions. And I want to first make sure that we know how to use the graphing calculator. So I've included a set of instructions here for the different types of functions, and we're also going to talk about the domain. Okay, so first, if you get your calculator or use your online calculator, I'm going to walk you through the steps of graphing these functions, starting with the linear function. The linear function is any function f of x is equal to x or 3x plus 2 or anything like that. Press y equals and type in x, and you get the graph of the basic linear function. This is y equal to x. I'm going to capture this. And remember that you can also use the function here to graph other types of linear functions. For example, I could edit this function to say y equals to say 3x minus 5, and that would be a linear function also, and graph it and see how it looks. Okay. So it's not restricted only to y equal to x, but y equal to x is the basic family. And next we can talk about the square or the quadratic function. Let's move this up a little bit so we have some space. Okay, the square or the quadratic function. So again, we go to our calculator. Y equal, clear it, and press x squared. And this is the basic quadratic function. And you can capture that, place it into the notes. Nope. Let's make sure that it has the designation on it. So I'm going to put that part in and then copy it. Okay, much better. So this is our basic square function. Okay, anything that has a square in it is a quadratic function. For example, if I were to modify this function and say this is x squared plus 2x minus 5, I would get a quadratic function also. It would be a U-shaped function like that. So it's not anything that has a square in it is regarded as the quadratic function. Not necessarily, but belongs to the general group of functions that occur in our classes. Next, we talk about the square root function. So y equals, clear your page, and press second and the x squared button to get the square root. Type in your variable and graph it. And this is your basic square root function. Capture that, put it in. In case you missed the instructions are written here expressly for the calculator, so you can go back later on and work on them. Yep. That didn't come out right because I need to have the okay, that's better. So I can just delete this one and put in a new one. Next, we're going to talk about the cube root function. So the cube root function is sort of a flat S-shaped function. To get this function, we press y equal, clear it, and press the map button and select number 4. And that's your cube root function, and graph it. Okay. Then the cube function is x to the power 3. We would go back, clear it, press X, dunce gap 3, and graph it. And this is sort of an upright backwards turned S. Kind of easy to mix up the cube and the cube root function, so be careful when you're doing that, okay? Next, the reciprocal function. This is sometimes called the rational function. Okay, this is the basic reciprocal function. A rational function could be any function over another function. So this is the basic family here, 1 over x. Graph that with your calculator. Simply type in 1 divided by x and graph it. And the last family, the last major family, is the absolute value function. So y equals, clear it. Press, you want to access absolute from the catalog. So second and the 0 button, and select the first item that you see there, and type in your variable. Get out of the absolute sign by moving forward, and graph it. And this is the absolute value function. So we're going to also be dealing with another type of function later on in chapter 3.1, which is called the piecewise function. I'm not going to discuss that right now. So hopefully this is not your first experience knowing about these functions. We're going to talk about the domain here. Okay? Domain. And domain, as we recall, is the complete set of the independent variable for f of x equal to some function. Okay? All right, now, good news. The following functions have a domain of all real numbers, the set of all real numbers. That's the set builder notation, or this can also be written as negative to positive infinity. You should know how to write both of these notations because your homework may ask you to use one or the other. Okay? And those functions are: one, all linear functions; anything in the form f of x is equal to x, or f of x equal to mx plus b, have a domain of negative to positive infinity. Any square or quadratic functions, anything in the form f of x equal to x squared, or f of x equal to ax squared plus bx plus c, anything in that quadratic form has a domain of negative to positive infinity. Any absolute value function, f of x is equal to the absolute value of x, or any variation of that, f of x equal to x plus some number. Any variation that's in an absolute value sign has a domain of negative to positive infinity. Any cube root function, anything in the form f of x is equal to the cube root of x, any variation of that still has a domain of negative to positive infinity. And any cube function, which is f of x, the basic form is x cubed, or it could be f of x equal to anything with the highest power that is x cubed. Anything where the highest power is x cubed is considered to be a cube function. So these five families, linear, square, absolute, cube, and cube function, all have a domain of negative to positive, or infinity, or all real numbers. Now that leaves us the reciprocal function. We're going to speak about that separate, domain of the reciprocal or rational function. Okay, and this is based on the premise that we cannot divide by zero. Hopefully you guys watched the video in the getting started module about why we can't divide by zero. So that means x cannot, in this particular function, the domain is any number, all real numbers except for zero. Not a way to write that is from negative infinity to zero. We jump over zero and continue to positive infinity. If the function looked like, say, f of x is equal to x plus 7 over x minus 3, if we set the denominator equal to 0, we get x is equal to 3. That is the exception. In other words, the domain cannot have 3 in it, because if we substitute back 3 in the denominator, we would be dividing by 0. So the domain of this function is that x cannot equal to positive 3, or from negative infinity up to 3, jump over 3 and continue to positive infinity. If we have, say, f of x is equal to x squared plus 7 over 2x minus 5. So let's say 2x plus 5, and we set that denominator equal to 0, we get x is equal to negative 5 over 2. This means that the domain x cannot equal to negative 5 over 2, because if we substituted negative 5 over 2 into the denominator, we would get 0, okay? Think about it. If we put back 2 times negative 5 over 2 plus 5, we get negative 5 plus 5, which is equal to 0, and that means we would be dividing by 0. X can be any number except for negative 5 over 2. So when we get to negative 5 over 2 on the number line, we have to jump over it and continue to positive infinity. More examples. Notice this has nothing to do with the denominator, okay? X plus 9 over x squared minus 16. So what happens there is if we set x squared minus 16 equal to 0, we get x squared is equal to 16, so x is equal to plus or minus the square root of 4, which is square root of 16, which is plus or minus 4. This has two numbers. If we substituted positive 4 or negative 4, we would still have a domain exception. So domain all x such that x cannot equal to plus or minus 4. In other words, from negative infinity to negative 4, following the number line, from negative 4 to positive 4, and then from 4 to infinity. One final example, f of x is equal to 9x squared over 3x squared plus 1. Notice in this case there's no number that you can substitute in the denominator that would make the denominator 0, because every time we square a negative number it becomes positive. So this denominator is always positive. Meaning that this domain is all real numbers. Or negative to positive infinity. Okay. So we also want to consider the square root function, which also has a domain that is not negative to positive infinities. The domain of the square root function to find that domain, since we cannot find the square root of a negative number, therefore the radicand must be greater than or equal to 0. The radicand is the part underneath the square root sign. That radicand must always be a number that's greater than or equal to 0. So if we have to find the domain of f of x is equal to 2x minus 10 square root, all we would need to do is set 2x minus 10 greater than or equal to 0 and solve it. And we see that x has to be greater than or equal to 5. That is the domain. The domain is all x such that x is greater than or equal to 5. Or from 5 to infinity. Bracket, parenthesis. Or we might have something like f of x is equal to the square root of, say, 10 minus 3x. So it's set 10 minus 3x greater than or equal to 0. Take away 10 from both sides. We have 3x greater than or equal to negative 10. And then dividing both sides by negative 3, we have x, and we have to flip the inequality. X is less than 10 over 3 positive. So the domain in this case is all x such that x is less than or equal to 10 over 3. Or from negative infinity up to 10 over 3. One final scenario here. If I have f of x equals to the square root of 15 over x plus 7. So this is a rational function underneath a square root sign. So we use the property of square roots to split it into two separate square roots. And we're interested in the denominator. So although on the denominator, we cannot take the square root of a negative number, but we can take the square root of 0. But if we were to get 0 on the denominator, in this case, if we were to substitute negative 7 in the denominator, then we would have the square root of 0, which is equal to 0. Okay? So in this case, we can't take it plus from greater than or equal to. We only need to take it greater than. So x can be equal to all numbers that are greater than negative 7. But not equal to negative 7. Because if we substituted negative 7 in that equation, we would be dividing by 0. So when you write this answer, if you're using interval notation, use parentheses instead of brackets on the negative 7. Next we can talk about combining functions. So the second part of this is to do function operations. So if we're adding two functions, we would simply add the two functions as a function of x. If we're subtracting functions, same process, except we would subtract the two functions. Multiplying functions, we would multiply the two functions as a function of x. And dividing functions, we would divide f and g as a function of x. Now, the first three cases are comprised of the domain of the original function. domain reflects the domain of the original functions. In this case, we have to consider the original functions. So domain would be the original functions domain as well as any values that make the denominator equal 0. Okay, so let's go ahead and see what they're talking about here. If I'm given two functions, okay, example, given f of x is equal to, say, 4x plus 7, and g of x is equal to 9x minus 2. And notice the domain is negative to positive infinity, because these are linear functions. Now, let's do the operations for all four. F of x plus g of x is simply adding the two functions, 4x plus 7 plus 9x minus 2, which is equal to 13x plus 5. The domain is negative to positive infinity, or all real numbers. F of x minus g of x is 4x plus 7 minus 9x minus 2, which is 4x plus 7 minus 9x plus 2, which is minus 5x plus 9, which also has a domain of negative to positive infinity. If we're multiplying them, f of x times g of x, 4x plus 7 times 9x minus 2, we would do FOIL on this. So this is 9 4 is 36x squared minus 8x plus 63x minus 14, and then combine it into a single, any like terms here. So this is 36x squared plus 55x minus 14. Okay, let me just box these so you can see them clearly. This has a domain of negative to positive infinity. It's a square function anyway. And if we were to divide the functions, f of x, g of x, we would be putting 4x plus 7 over 9x minus 2. So if we set the denominator equal to 0, we would get x is equal to 2 over 9. In this case, the domain is all real numbers except for 2 over 9, cannot equal to 2 over 9. In other words, from negative infinity to 2 over 9, jump over and continue to positive 2 over 9. The questions may also ask you to substitute numbers. For example, it could ask you to find, let's number these parts, A, B, C, D. Part E might say F plus G substituted with 4. So you would take the F plus G function, which is 13x and substitute 4 in there, 13x plus 5, and get 57. Or part F might ask you for f minus g substituted with 2. So I will take the negative 5 times 2 plus 9, which is equal to negative 1. The g part might ask you to substitute f times g substituted with, say, 3. So this is 36 times 3 squared plus 55 times 3 minus 14. I put that in my calculator and I got 475. And h part might be f over g substituted with, say, 1. So this is 4 times 1 plus 7 over 9 times 1 minus 2, which is 4 plus 7 over 9 minus 2, which gives a fraction, 11 over 7. So these problems have several parts. Please be careful. Pay attention to what you're doing in them. I'm going to do a second example of combining functions. This one, we're given, say, f of x equals to 7x plus 9 over 9x minus 7, and g of x is equal to 9x over 9x minus 7. Notice if we set the denominator 9x minus 7 equal to 0, we get x is equal to 7 over 9. So the domain is all x except for 7 over 9. Same for this one, because the denominators are the same, which is a great thing. So part A, f plus g is 7x plus 9 over 9x minus 7 plus 9 over 9x minus 7. So since the denominators are the same, we would just combine the numerator and keep the same denominator. That gives us 16x plus 9 over 9x minus 7. Notice the denominator is the same as for the original functions. To the domain is still x cannot equal to 7 over 9. If we were subtracting the functions, f minus g, we would have 7x plus 9 minus 9x over 9 minus 9x minus 7, which comes out to be negative 2x plus 9 over 9x minus 7. Domain x not equal to 7 over 9. Okay, I should be boxing these answers. If we were multiplying the function, f times g, we would have 7x plus 9 over 9x minus 7 times 9x over 9x minus 7. In this case, we would need to do FOIL. So this would be 9x into 7x plus 9. And if we FOIL the denominator, we have 81x squared minus 63x minus 63x plus 49. Distributing the numerator, I have 63x squared plus 81x. And on the denominator, I have 81x squared minus 126x plus 49. the domain here still remains the domain of the original functions. X is not equal to 7 over 9. There's no need to set this denominator equal to 0 because we know that the domain for the first three cases must be the domain of the original functions. Now, it gets a little messy when we come to part D, which is f divided by g, which is 7x plus 9 over 9x minus 7 divided by 9x over 9x minus 7. So this is where you would use the keep KFC rule, which is keep the numerator flip the denominator over and change the sign to multiply. Notice that it cancels out 9x minus 7. So I have 7x plus 9 over 9x over 9x. Now, we've got a little problem here because this denominator, x cannot equal to 0. So be careful because the domain is all x. X cannot equal to 0. And in addition, from the original functions, x cannot equal to 7 over 9. So two exceptions to the domain. Even though that's not shown in this function, we still have to go with what the original function says. The remaining four parts of the problem are going to ask you to substitute numbers, so I'm sure you guys are in good hands with that. I'm not going to do that. All right, this is a pretty long chapter. The final thing I need to discuss here with you is the difference quotient of a function. The difference quotient of a function. Difference quotient, dq, is given by the formula fx plus h minus f of x over h, where h cannot equal to 0. So I want to make sure that that we know how to find a difference quotient. So let's take a simple example here first. Example. Find the difference quotient of f of x equals to negative 2x plus 3. In order to use our formula, we need to find fx plus h. We already know what fx is, f of x is over h. So let's find fx plus h. All we're asking here is that wherever we have an x, we substitute x plus h. Distribute, we have negative 2x minus 2h plus 3. So we have the parts that we need to substitute now into this equation. Into this formula, we have fx plus h is negative 2x minus 2h plus 3 minus the original function, which is negative 2x plus 3 divided by h. So this is negative 2x minus 2h plus 3 plus 2x minus 3. As a hint to you, when you're doing a problem like this, everything that does not have an h should cancel out. By the way, this is over h. So negative 2x cancels out with positive 2x, 3 cancels out with 3. And this leaves us with negative 2x over h. Cancel out the h's and we get the answer is negative 2. The goal is that when we simplify this, we're able to cancel out the h on the denominator because we can't divide by h in the formula. And then remember what I told you, when you're simplifying this part, you should be able to eliminate everything that does not have an h. Let me pick up maybe one or two more examples here with you. How about find the difference quotient of f of x is equal to x squared plus 2. So first we would find fx plus h, which h cancels out, and I get my answer is I think I made a mistake here. Let me go back and fix this. Yeah. This is x squared plus xh plus xh plus h squared plus 2, which is x squared plus 2xh plus h squared plus 2. So the difference quotient, x squared plus 2xh plus h squared plus 2 minus the original function, which is x squared plus 2 divided by h. So this is x squared plus 2xh plus h squared plus 2 minus x squared plus 2 over h. So everything that does not have an x should cancel out. And this leaves us with 2xh plus h squared over h. Factor out h on the numerator, we have h into 2x plus h divided by h. So the answer is equal to 2x plus h. I wanted to catch one final example with you. Okay. Example. Find the difference quotient of f of x is equal to negative 3x squared plus 2x minus 5. Okay, so we start by finding x plus h, fx plus h, which is negative 3 into x plus h squared plus 2 into x plus h minus 5. From the previous example, we know what x plus h squared is. It's x squared plus 2xh plus h squared. Okay, we know that from up here. Plus 2x plus h minus 5. So now we go ahead and distribute the negative 3. Remember never to distribute that negative 3 before you do the parenthesis. Minus 6xh minus 3h squared plus 2x plus 2h minus 5. There are no like terms that are going to cancel here, okay? Now we use a formula. Difference quotient is equal to fx plus h minus fx over h. Substitute the entire expression for fx plus h, which is this whole mess here. We've got negative 3x This is 3x squared, sorry, 3x squared, negative 3x squared minus 6xh minus 3h squared plus 2x plus 2h minus 5, and then subtract the entire function, minus negative 3x squared plus 2x minus 5 all over h. So this is negative 3x squared minus 6xh minus 3h squared plus 2x plus 2h minus 5 plus 3x squared minus 2x plus 5 over h. Now remember what I said, everything that does not have an x should cancel, an h should cancel out. So negative 3x cancels with squared, cancels with positive 3x squared. 2x cancels with negative 2x, and negative 5 cancels out with positive 5. That leaves us with negative 6xh minus 3h squared plus 2h over h. Factor out the common h on the numerator. We have negative 6x minus 3h plus 2 divided by h. And that leaves us with our answers, negative 6x minus 3h plus 2.